Okay, so welcome everyone. My name is Matthias and I'm here with my two colleagues Adam and Stefan, and I want to give you a brief update on what's new in the L4Re operating system. For those who do not know us, we are from the company Kern Concept. It's a spin-off from the Technical University in Dresden, and in a couple of months we will celebrate our third birthday. It was founded by the core developers, and if you like you can go to our website to learn more about us. So for those who don't know what L4Re operating system is, I just want to give a very brief overview of what is the system, and it's mainly composed out of three components. And the first one is the L4E microkernel. It is of the L4 family, and for most of the people it's known as Fiasco OC. We refer now to this as the L4E microkernel because if you are meeting a customer in the first place, Fiasco may not be the first name you want to tell him. Then we have the L4E runtime environment, which is a set of components which allow you to build systems. So you have a memory manager there, an I/O manager, a root task, and some other components which you are required to have to build a real system. Then of course, to actually build something useful, you need drivers and other services. For example, if you're doing some security applications, you may have some signing services or crypto services running on the system. And the third major component in our system is L4Linux, which is the Linux kernel running as a user space application on top of the microkernel. The way it works is that instead of using hardware services, the L4Linux kernel uses the mechanisms and the API of the microkernel to actually provide its standard Linux services. Then our microkernel supports hardware virtualization or hardware assisted virtualization. I will come to that back later. Then a very fairly new topic are these so-called library OSs. We can support that as well. And of course you can have native applications running on the microkernel and using services from the runtime environment. So the key features of our system is, so first of all, it's not a fully fledged operating system in the sense that you're, as an end user, can take it and download it and install it onto your machine and then be happy for the rest of your life. No, instead it's a set of building blocks which allow you to build systems. We have a broad support from third-party code, so third-party packages like Python. We have a fully fledged C++ standard library. You can run SQL on it. We have a port of the Cairo library and some basic POSIX compatibility like pthreads, for example. So that makes porting existing software to our system a little bit easier. L4E itself is very or highly modular, which means that in our system everything is handled like, or is an object. So starting from basic kernel services which are considered as objects and their interfaces which are uniform across the system. So for example, you can build proxy services. So you have scheduler in the kernel, and this scheduler is exported via the scheduler API. And then in user space, you can have a scheduler proxy, which, for example, allows other components to use this scheduler API and implement different scheduler strategies for their clients. Another key feature is our broad platform support, so we support x86 and 32-bit and 64-bit mode. ARM is supported, and yeah, we have a multi-core support, so SMP support, and as I already mentioned, we support hardware-assisted virtualization. And right now our system is used on the broad range of hardware, so starting from embedded systems like mobile phones or even yeah, small ARM boards like the Raspberry Pi to fully fledged x86 server systems like the 19-inch racks. User and kernel, or the user space, so the runtime environment and the kernel, they are developed in developed closely together. So there's always a close connection between those. And to some extent, we allow to the system designer to choose between dynamic setups where you can create tasks and processes dynamically and destroy them, as well to some sort of static setups where these feature set is restricted. So you just basically boot up the system, and then during runtime you're not allowed to start any more processes in the system. So actually, what's new in the system? So I will go through the 3 components, and I will tell you for each of the components what are the major new features we implemented during the last year. And yeah, as the title of the talk already said, it was kind of facing the reality. So we got a lot of requests and input from our customers. So that was the main force, the main driving force behind our development. So we started the lowest layer with the microkernel here. On the ARM side, we added hardware-assisted virtualization support. I will come to that later and tell you a little bit more about it. And we added support for a new system on a chip to Fiasco. So the Allwinner SoC, which is, for example, used on the famous QB board, is now also supported. So you can use that board as well. And then from Texas Instruments, we added support for the OMAP 5, which also has these hardware, ARM hardware virtualization extensions. So that was added to Fiasco. For x86, we made a huge step concerning suspend resume, which is the ACPI power management level F3. So Fiasco now can put the system to sleep, so store or suspend the state of the system to memory, and then later resume from that suspended state. We can now boot our system on UEFI platforms. So UEFI is the successor of the BIOS, and so it's getting more and more used in modern hardware on x86, and so we had to add support for that as well. And then last year we learned that it's always good to have some checkmark features for your system to increase security. And one of those features is SMAP. This is a feature implemented by Intel. It's called Supervisor Mode Execution Prevention. And it's a feature that you can set an attribute for a page that when run in in kernel mode, the kernel cannot execute code residing on that page. And this feature is present since Ivy Bridge CPUs from Intel, and Fiasco now supports that. Then major or an ongoing effort is extending and providing our tools support. So we have been working on Clang and LLVM support. This is still work in progress. It's sort of continuous effort because it's kind of a moving target. So is GCC 5 support. So GCC 5 hasn't been finalized yet, but since 2 weeks or so, GCC 5 isn't crashing anymore when it's trying to compile Fiasco. And this also led to the effect that part of Fiasco's source code is now part of the GCC 5 test suite. So Fiasco actually used a feature which triggered seg fault for GCC 5, and now they have fixed it. Yeah, and we are continuously working on supporting the latest compilers and binutils. This also leads to the unfortunate situation that, for example, the latest binutils from Debian, they broke the COF support, which is the Windows binary format, and you need that to actually support UEFI, because on UEFI platforms the binary format is not ELF but COF. So don't use the latest binutils right now. Yeah, what has happened in the runtime environment? Suspend resume is actually very useless if you only have it in the kernel, because in the microkernel system the policy is implemented in user space. So, and if nobody or no service is telling the kernel to suspend or to resume, then you actually cannot use it. This part is implemented in the I/O manager in L4Re. And we implemented a mechanism called inhibitor locks, so that clients can, for example, prevent a system going to suspend mode when actually there is going on some transaction or user interaction. We support ACPI events like button events or lid close events. So when you just close the lid of your laptop, the system can go to suspend mode and save power. And one of the key features is that it works with L4Linux. So when L4Linux, or when we use L4Linux as a driver, for example, to drive hardware, then L4Linux, for example, can, by using inhibitor locks, prevent going the system to suspend, or the I/O manager just can also send a suspend signal to Linux so that L4Linux instances can go to sleep. Then we enhanced and extended our I/O manager on other parts. So we now made the full transition to Lua as the configuration language for I/O. So what you can do now with Lua is that you specify the device tree for the platform. So if you are on ARM, you don't have something like ACPI, which will provide you a device tree. So you have to provide one on your own. And you also use it to create virtual buses where you can connect devices to and then hand those virtual buses to a client. So that's a sort of a virtualization layer for devices. We made big refinements to the GPIO multiplexing API because if you are working on an embedded board, one of the first systems or devices you need to get running is the GPIO interface or the GPIO device, because without that you are not able to switch on any other device present on the board, so like display or something like that. Then we added support for that you can assign a GPIO pin, so a single GPIO pin as a resource to a device. So that essentially means that we can virtualize GPIO chips on a per pin level. So if a GPIO chip, for example, provides 32 pins, and you want to have different clients using different pins from this same GPIO chip, previously you had to share them, but now I/O can virtualize them and put these single GPIO pins as a resource to a virtual device, which then can be driven by an isolated client. To prove that this implementation is actually working, we added driver for the Broadcom ARM SoC, which is present on the Raspberry Pi. And we have one single GPIO driver for the OMAP series. And then you can use Lua to configure that driver and use it on OMAP 3, 4, and 5. So no need to write specific driver for OMAP 3, 4, or 5, but instead you can just exchange the device tree specification, and then you can use it, for example, on OMAP 5. Another security feature we added to the system is the support for stack protector. That's actually a compiler feature which adds a so-called terminator canary to each stack frame whenever a stack frame is pushed onto the stack. And when you return from a function, for example, and you destroy an existing stack frame, then there is code checking for the presence of this terminator canary and whether it's still consistent. And if not, then the system assumes somebody compromised the stack, for example, using a buffer overflow, and then it prints an error message and the application is halted. So there is no way for an attacker to use a buffer overflow on the stack to gain control over the system. Then we added client library for wood.io support. So this is still ongoing work. So this library implements or provides the basic wood.io primitives like queues, rings, and the MMIO interface. And it allows you to implement the host side of a wood.io device, so basically the device emulation. And this looks like that. And we have the microkernel, the runtime environment, and one of the examples is now L4Linux. So in L4Linux, there is a console driver for wood.io. It then talks to the wood.io backend, and then we can use our client library, implement a console device, and it then is communicating through wood.io with the wood.io console device in Linux. And yeah, then for example, the console device can write to the kernel console and print it to the serial device, or you can use some other log services or whatever you want. And this also works with block drivers and network drivers. So it depends on the implementation of your device. Yeah, we made some big steps in the virtualization support in L4Re. First, of course, L4Linux. L4Linux is still broadly used today because you can also use it on platforms where you don't have hardware virtualization support. The current version is 3.18. 3.19 is expected to arrive in a couple of weeks. So this is a continuous update. Then, as you have seen on the previous slide already, we added the wood.io L4 backend, which actually implements the MMIO interface with our client library. Then we added a file system server, which allows you to export files to a client, and the client can then use this file as a file system. So for example, you can export partitions of a physical hard drive to clients, and then they can use those for persistent storage. The same way we added a frame buffer server. So this service exports the physical frame buffer for other clients, and this allows us, for example, to use the Intel i9015 graphics to enable the frame buffer there on such platforms. L4Android is kind of a side project from L4Linux, and it allows you to run Android on top of L4Linux. So we updated the images to the latest. At that time, it was the latest Android version, and a couple of weeks later, Android 5.0 arrived. So yeah, Lollipop is still work in progress. And on the website from L4Android, you can download a technology demo which showcases some of the features I already mentioned. So this is a screenshot of the L4Android demo running in QEMU. And you see here 2 instances of Android running in parallel. You can see that there is some sort of virtual power device, so the battery is actually displaying a certain status. In behind, so you cannot see it here, there is running the file system servers, so these Android instances have persistent storage, so you can change the settings, and upon reboot they're still the same. Last year we already mentioned L4KVM as a virtual machine monitor to be used on our system, and the requirement was that we need a feature-rich virtual machine monitor, and feature-rich in that case means that it can or is able to run Windows. So unlike for Linux, you need to fully emulate the PC platform in your virtual machine monitor to support Windows, because you cannot modify the sources. And L4KVM is a mechanism to use KVM from within L4Linux. The status of that is that we now have x86 support, so for AMD SVM and Intel VTX. It runs on 32-bit and 64-bit host systems, and it supports nested paging, so the performance is very good. The way it works is that the virtualization support is implemented in the microkernel, so the microkernel actually makes the world switch between the root mode and the non-root mode. Then we have L4Linux and the KVM module, and every time KVM tries to execute a privilege instruction to, for example, modify the virtual machine state or the virtual machine control structure, we had to replace that using L4 specific or L4Re specific mechanisms. And then on top of L4Linux, you run QEMU as the VMM or provider for device resources for the virtual machine. And so QEMU tells KVM what to do, and KVM then writes the correct setup for the virtual machine into the control structure. Then we switch into the microkernel. The microkernel does the world switch, and we end up running in non-root mode as in a virtual machine. So the biggest news possibly is the support for ARM, hardware-assisted virtualization. And if you have a look at the existing architecture on ARM, we had basically two privilege levels, so user mode and supervisor mode. And there we were running the kernel and the user land. And of course, ARM calls this the non-secure world. And if there is a non-secure world, there must be some other world, so the secure world. And this is also known as trust zone. And on the secure side, you usually have some sort of trusted OS with trusted services, so whatever that means. And that was the picture till then. And when you wanted to make a transition between the non-secure and the secure world, you had to issue some so-called secure monitor call. And then you were going through this monitor mode, which is some assembly code, which actually just switches between those two worlds. But the picture has changed when ARM virtualization support arrived. So they added another privilege level, PL2, or sometimes it's also referred to as HIP mode. And then you can run an hypervisor there. And yeah, PL0 and PL1, it basically remains unchanged. But now you can, using the hypervisor, run multiple kernels and multiple user lands as a virtual machine on top of the hypervisor. So, and in L4Re, or on top of our kernel, the picture looks like this. So we have the L4Re microkernel running in HIP mode in PL2. Then we have a small virtual machine monitor which runs in PL1, and it switches between the virtual machine, which is this dotted gray box here on the left, and depending on the state of the virtual machine, it will switch either into the kernel mode PL1 for the virtual machine, or into user mode PL0 of the virtual machine. And besides that, you can still run native L4Re applications. But there's a problem, and the problem is booting. The problem is then if there is some secure software installed on the trust zone side, then usually the platform boots in non-secure PL1 mode, and this doesn't allow you to switch down to PL2 mode, so into the HIP mode. So yeah, the question is how to get to PL2 mode. And the other problem is if there is no secure software installed, you get booted into the secure mode, and the HIP mode is only available in non-secure mode. So what can you do? So the first key is you need support from the secure side. And the first solution is that you use the secure side and let it switch to PL2 mode. So this would work like this. We run Fiasco, the L4Re microkernel, as a trust zone enabled kernel. This is possible. And then we can use it to switch through the monitor mode into the PL2 mode. And then we run Fiasco in HIP mode. And then we can have the VMM there, and the VMM then drives the VM. The second solution is, okay, we need support on the secure side, that we get launched in the non-secure PL2 mode. So, but this also requires support on the secure side. Then the picture looks like this. There is some trust zone enabled U-boot installed on the platform, and it allows kernel to be launched in PL2 mode, and then we can set up the VMM and run VMs on top of the microkernel. So how's the status? Yeah, it's supported by our microkernel. We tested it on two platforms, which are the Exynos 5 and the OMAP 5 CPUs. And yeah, the platform boot is the key. So if you have a platform or an SoC where hardware virtualization is implemented, you still need some support from the hardware vendor that you are able to switch into PL2 mode. And then we have an accompanying VMM in the package VMM. So this already is public, and you can go ahead and try it out. In the next part of the talk, I will sort of try to step back a little bit, because last year we not promised, but thought about the next steps which we think are relevant over the course of the next 12 months. And So for the microkernel, we said, okay, we're working on EFI support, and yes, it's there, so we can boot on EFI platforms, at least on x86. So probably in the future, we will also get EFI on ARM platforms, but they haven't materialized yet. Yeah, on the tools front, we bumped the minimal required GCC version to 4.5 for Fiasco. Clang is still work in progress, so we are wiping out the last GCC specific parts and trying to work around compiler specific characteristics. This is still a continuous effort. So recently we had to add compiler blacklists because we were bitten by some serious compiler bugs, and so we just, as a safe feature, we blacklist them now, and you're not able to actually compile Fiasco with certain compilers or compiler versions. So yeah, we are working on this as well. In L4Re, one of the major features is power management. This makes the system actually usable, for example, on a laptop, because now you can just close the lid and put it in your backpack, and so you get basically the same power characteristics like on a Linux system. On virtualization, we added ARM virtualization support. I think it's one of the major features there. We re-enabled and extended L4 KVM support, so on 64-bit x86 hosts, we are also capable of running, for example, 32-bit guests, which I think is a big feature. Then last year we talked a little bit about L4 Linux 64-bit. This is still experimental, so we haven't released it to the public yet, because merging it with the existing 32-bit port is not so easy, so there are some design changes internally which needs to be worked out. And we also updated L4 Android, which has gotten some rust last year. So I want to close the talk by giving some sort of outlook into the future. So what do we think is important or may become important over the next year? And on the microkernel side, we think ARM 64-bit is becoming important, because now major SoC vendors are providing hardware with ARM 64-bit or ARM 64 enabled CPUs. On the security front, we think I/O MMU support may become critical, and those two features also require some user space support, and at least the I/O MMU support incurs some design decisions which need to be discussed and then at some point in time eventually taken. And probably more static configurations of the system, so where you have even less dynamics, which you nowadays have, may become interesting for some high assurance, high security applications of the system. In the user land, there is some big work going on an RPC framework. We all know that writing client-server applications using IPCs at some point in time becomes difficult and cumbersome. And we also have seen a lot of bugs or implementation bugs using the existing I/O streams. So I/O streams are fine, they're easy to use, and they are somehow natural for C++ developers. But we have seen, for example, a server putting an int into the I/O stream, and then the client taking out a long or reading a long from the I/O stream. So this is okay on 32 bits, but if you're going to 64 bits, it will blow. So yeah, there is some RPC framework. It will be based on C++ mechanics using templates and some basic macros. This is still work in progress, but it will ease a lot implementing interfaces on client and server side. Then there is ongoing work on a native AHCI driver. Then we've made internally already the transition to Lua 5.3. This was a big relief for us because now Lua supports real integers and bit operators. So previously we were using Lua 5.2 and integers were represented as floats. And if you are using we are using Lua in I/O, and if you want to specify a 64-bit memory address, you had to use a string, and then you had to convert that string back to a number. So yeah, now we have real integers, and they are 64-bit wide, and that helps us. A big topic we don't have done too much on this front yet is application debugging. So ideally, you have something like GDB. You can hook it up to your graphical GDB interface in Eclipse, for example, and then you can debug your user space applications. So we think that we will need something on that as well to foster development of applications and programs on L4Re. And we are also working to extend the tool support for L4Re, so Clang. So we started compiling the L4Re userland with Clang as well. There are a lot of bits and pieces which need to be nailed out, and also GCC 5 will become important over the next year. On L4 Linux, we are working, or we are looking into supporting device trees, at least on ARM. And the hope there is that it shall help device enablement on ARM, so that you can provide a device tree to L4 Linux, and then you can use L4 Linux to drive devices on ARM platforms. If you're interested to learn more and see what's going on, I provide you a few resources where you can go. You can talk to us here around. We are still the end. We are here still the end of the conference. And that's the end of my talk, and I'm happy to take questions from the audience. So I will take, or I will answer the second question first. So actually, the L4 Linux kernel runs in its own address space, and it's a single address space, and each of the Linux processes created by Linux also run in its isolated address space. Yeah. So. Yeah, but you can enable these protection mechanisms in Linux. So, for example, you can use address-based layout randomization on top of L4 Linux. So, for example, when we run Android on top of L4 Linux, Android implements address space layout randomization and then and non-executable memory. So it's just a feature you need because L4 Linux still manages the page tables for its processes, and if the memory management subsystem of Linux marks pages as, for example, non-executable, it will use the map call from the L4 microkernel and provide those bits to the kernel, and then the kernel will actually set the bits in the page table. And the first question was regarding how does the power management and suspend works. So as I mentioned, we implemented something called inhibitor locks, and in the microkernel there is a new object called the platform control, which in the end will switch or suspend the system to RAM. And the way it works is, so let me start, that for example a driver has a reference to this suspend, to this inhibitor lock, and it says lock because it's, for example, starting a file system transaction, so it's trying to read blocks from a disk. And then during that time, for example, an ACPI event arrives, so the user closes the lid. Then there is a system manager which manages suspend resume in the system, and this event gets sent to the system manager. So the system manager says, okay, suspend, and because IO in this case is the central instance here, gets the suspend call, and the system manager does not know yet the state of the system of all the clients, whether they are ready to go to suspend or whether they have some in-flight transactions going on. So IO will send the suspend event over this inhibitor lock to the clients registered with this inhibitor lock. And then the client has to say, okay, I release this lock because my transaction is done, or I've just canceled the transaction, and actually signals to the system, okay, for me now it is safe to go to suspend mode. And if that's the case, then IO tells the platform control object, okay, it's safe to suspend, and then Fiasco stores all the state it needs to memory and actually suspends the system. And when you resume, you get some other event, so it's going through the ACPI mechanism, and then Fiasco will actually reinitialize every CPU and just resumes as it was before the resume call. Does it answer your question? Okay. Yeah. So from the perspective of the VM, KVM, or in that case the whole L4 Linux, the L4 Linux kernel has to be trusted because it manages the resources and the state switches for the VM. This is a runtime thing actually. So you provide a piece of Lua code or Lua script which is handed over to IO, and then IO parses this Lua file, actually executes in the Lua environment, and then, for example, dynamically creates the device tree. During at this point in time, it's done during boot. So when IO starts, it gets handed over the device tree specified in Lua, and then it will create all the devices. There was another question? Yeah. Sorry, I didn't get the question completely. Yeah. No, I think all the today's L4 kernels just carry the L4 in their name, and they're not compatible in any way any longer. So back 10 years ago or so, there were some formal specifications for the API and stuff like that, but that's not the case anymore. So they're just, as Gano showed this morning, it's a tree and it's split off, and I don't think we can actually really borrow code from SEL4 because SEL4 uses a high level language, going from the Isabelle specification, using Haskell and stuff like that, and then they create actually the C code, and that doesn't help us.
Thank you very much.
Thank you.